In this video, we're going to talk about how to solve integrated rate law problems. So if you have a pen and a sheet of paper with you, feel free to use them to take down some notes, which is going to be useful later on as we work on some problems in this video. So let's begin our discussion with the rate law expression for each of these ordered reactions. So for a zero order reaction, the rate is equal to K times A raised to the zero power. Anything raised to the zero power is 1, so the rate is simply equal to K. A is a reactant, so think of a reaction where, let's say, A turns into B. So A is the reactant and B is the product. So for a zero order reaction, the rate of the reaction doesn't depend on the concentration of the reactant. For a first order reaction, the rate does depend on the concentration of the reactant. Its rate is equal to K times A raised to the first power. For a second order reaction, the rate is equal to K times A raised to the second power. So the order of the reaction is based on the exponent that you see here. Now, for a first order reaction, if you double the concentration of A, the rate is going to double. If you triple the concentration of A, the rate is going to triple. For a zero order reaction, if you double the concentration of A, it's going to have no effect on the rate. If you triple the concentration of the reactant A, no effect. 3 to the 0 power is 1. For a second order reaction, if you double the concentration of A, 2 squared is 4. The rate is going to increase by a factor of 4. If you triple the concentration of A, 3 squared is 9. The rate is going to increase by a factor of 9. So the order of the reaction, or rather the order of the reactant, tells you how the concentration will affect the rate. The rate of the chemical reaction is most affected by a reactant that is second order compared to a reactant that is first order or even zero order. So the higher the order of the reactant, the greater its impact will be on the rate of the reaction. Now let's talk about the units of the rate constant K. So the units of K for a zero order reaction is going to be m to the first power times T raised to the negative 1. Now, T is a unit of time. It could be seconds, it could be minutes, it could be hours, it could be even days. But T is some type of unit of time. Now, for a first order reaction, it's going to be m to the 0, T to the negative 1, or simply T to the minus 1. For a second order reaction, the units of K is going to be m to the negative 1, T to the negative 1. Notice what's happening to the exponent of m as you increase the order of the reactant. It's decreasing by 1. So for a third order reactant, it's going to be, the units of K will be m to the negative 2, T to the minus 1. So we can come up with a general equation that will tell us the units of K given the order of the reaction. And here it is. It's m raised to the 1 minus n times T to the negative 1. So that's the units for K for any order. So let's say if it's second order, n is 2. So this is going to be m raised to the 1 minus 2 times T to the negative 1. 1 minus 2 is negative 1, so you get this. So this expression is very useful in determining the units of K given the overall order of the reaction. Now the next topic of discussion is the half-life. So the half-life is a unit of time. So it's going to be T with a subscript 1/2. And that's the time it takes for the concentration of a reactant to decrease by half of its original amount. For a zero order reaction, the half-life is going to be the concentration, let me write this better. It's going to be the concentration of A, more specifically the initial concentration of A, divided by 2k. For a first order reaction, the half-life is going to be ln2 divided by k, where k is the rate constant. And for a second order reaction, it's going to be 1 over k times the initial concentration. So what you want to gather from this is that the half-life for a first order reaction doesn't depend on the initial concentration. For a zero order reaction and a second order reaction, the half-life depends on the initial concentration. But for a first order reaction, it's independent of the initial concentration. Make sure you write that in your notes too, because that's a typical test question. Now, in all cases, the half-life depends on the rate constant k. And notice that k is always in the bottom of the fraction for the half-life equation. So that means for all cases, as the rate constant increases, the half-life will decrease, regardless of the order of the reaction, if it's zero, first, or second order. Now for a zero order reaction, if we increase the initial concentration, the half-life is going to increase. So for a zero order reaction, the half-life is directly proportional to the initial concentration. Now the reverse is true for a second order reaction. If we increase the initial concentration, the half-life decreases. So the initial concentration and the half-life for a second order reaction is inversely related. For a first order reaction, if you try to increase the initial concentration, it's going to have no effect on the half-life. The half-life is not going to go up, it's not going to go down. The half-life is independent of the initial concentration for a first order reaction. Now let's talk about the equations for the integrated rate law expression. Now it's going to be tough fitting it in here, so I may have to erase it after I write it. So hopefully you have a sheet of paper and you can write it down, because we're going to refer back to these equations. So for a zero order reaction, the final concentration is equal to negative kT plus the initial concentration. So that's the integrated rate law expression in slope-intercept form. Y corresponds to the final concentration, M corresponds to negative K, X corresponds to T, and B corresponds to the initial concentration. So notice that the slope is equal to negative K, and the y-intercept is equal to the initial concentration. So make sure you write this equation. So for the next part, I'm going to put the slope, because you want to know that as well. So for a zero order reaction, the slope is going to be negative K, as was mentioned. Now let's talk about a first order reaction. The integrated rate law expression for a first order reaction is the natural log of the final concentration, and that's going to equal negative kT plus the natural log of the initial concentration. So once again, this is in slope-intercept form. So as you can see, the slope is still negative K. The y-intercept this time is the natural log of the initial concentration. So we can write M is equal to negative K for a first order reaction. Now for a second order reaction, it's going to be 1 over the final concentration, and that's going to equal positive kT plus 1 over the initial concentration. So this too is in slope-intercept form. So we have y is equal to mx plus b. So this time the slope is equal to not negative k, but positive k. And the y-intercept is 1 over the initial concentration. So we're going to put m, the slope, is equal to positive k. Now the next thing that you need to know is the plot that leads to a straight line graph. For a zero order reaction, it's simply the concentration versus time. For a first order reaction, if you plot the natural log versus time, you're going to get a straight line. And for a second order reaction, you need to plot 1 over the concentration versus time. And the formula pretty much tells you that as well. So here's the graph for a zero order reaction. You need to have the concentration of A on the y-axis, T on the x-axis, and the graph is going to look like this. Because as you can see, the slope is negative. K is always positive, but because the slope is negative k, you can see that it's a decreasing function with a straight line. Now for a first order reaction, if you were to plot the natural log of A versus time, you would get a similar shape. It's going to be a straight line graph with a negative slope. For a second order reaction, if you plot 1 over A versus time, it's different. This is going to be a straight line graph going up. So as you can see, the slope is positive k, so that's why it's an increase in linear function. Number 1, which of the following could represent the units of the rate constant k for a reaction that is third order overall? Is it going to be A, B, C, or D? So go ahead and take a minute and try this. We know the units of k can be represented by this formula, m raised to the 1 minus n times t to the minus 1, where n represents the order of the overall reaction. So this reaction is third order overall, therefore n is going to be 3. So it's m raised to the 1 minus 3 times t to the minus 1. 1 minus 3 is negative 2. So the units for a third order overall reaction should be something to this effect: m to the minus 2, t to the minus 1. And this corresponds to answer choice C. So that's the answer for this problem. T could be anything. It could be seconds, minutes, hours, days, but it's some unit of time raised to the minus 1. Number 2. Which of the following straight line plots correspond to a first order reaction? So hopefully you have your sheet of notes with you if you haven't memorized it already. But let's review the zero order reaction. So if you recall, for a zero order reaction, if you plot A versus T, you're going to get a straight line graph. And the slope of that graph is going to be negative k. So A versus T corresponds to a zero order, not a first order. Now for a second order reaction, the graph 1 over A versus T produces a straight line plot. And the slope for that is not negative k, but positive k. So we could eliminate answer choice C. 1 over A versus T will not produce a straight line plot for a first order reaction. For a first order reaction, the graph that we need is ln A versus T. It's the natural log versus time. When we plot ln A on the y-axis, time on the x-axis, we're going to get a straight line plot with a slope of not positive k, but negative k. So the correct answer is let me say that again. The correct answer is answer choice D. The slope is going to be negative k, and the graph is ln A versus T. It's not positive k. Number 3. Which of the following statements is false? So let's analyze each choice. Answer choice A. The half-life of a first order reaction is independent of the concentration of the reactant. Is that true or false? So hopefully you have your sheet of notes with you, and let's look at the half-life equation for a first order reaction. The half-life is equal to the natural log of 2 divided by the rate constant K. Notice that the initial concentration of A is not part of this equation. Therefore, answer choice A is a true statement. The half-life is independent of the initial concentration of the reactant. Now let's look at answer choice B. The rate constant K is inversely related to the half-life of a second order reaction. Is that true or false? Well, if you have your sheet of notes with you, let's look at the equation. So the half-life equation for a second order reaction is this. It's 1 over K times the initial concentration of A. Now notice that the rate constant K is in the denominator of the fraction. Whenever you increase the denominator of a fraction, the value of the whole fraction goes down. So as we increase the rate constant K, the half-life is going to decrease. So when K goes up, the half-life goes down. So this describes an inverse relationship. So therefore, B is true. The rate constant K is inversely proportional to the half-life for a second order reaction. Now what about C? The half-life of a zero order reaction is directly proportional to the initial concentration of the reactant. Is that true or false? So let's begin by writing the equation. So the half-life equation of a zero order reaction, that's going to be the initial concentration A divided by 2K. So we're analyzing the half-life and the initial concentration of the reactant. So we're comparing these two. Notice that the initial concentration of the reactant is in the numerator. Whenever you increase the numerator of a fraction, the value of the fraction goes up. If you increase the denominator, the value of the fraction goes down. So because the initial concentration is in the numerator, there is a direct relationship. As we increase the initial concentration, the half-life is going to increase as well. So there's a direct relationship between the two. So C is a true statement. These two are directly proportional. Now what about answer choice D? The half-life of a zero order reaction is constant. Is that true or false? So this is the half-life for a zero order reaction. Is this value, T1 half, is it constant? So T1 half depends on the initial concentration and K. This too is not going to change. That's constant. K is the rate constant of a reaction. The fact that it's a rate constant means that K doesn't change. That is, if the temperature doesn't change. So we're assuming that the temperature remains constant. If the temperature is constant, then K is going to be constant. So at constant temperature, K is not going to change. Now, the initial concentration, is that constant? Well, the answer is no, because the purpose of chemical kinetics is to study how fast reactions are going. And if the reaction is going, as A changes to B, A is going to decrease. So as the reaction proceeds, the concentration of A will not be constant. It's going to decrease over time. So if A goes down, the half-life is going to go down with it because they're directly related. So therefore, the half-life of a zero order reaction is not constant. So this is a false statement. Therefore, D is the correct answer choice. So note that the half-life of a zero order reaction and a second order reaction depends on the initial concentration of A. Therefore, the half-life is not constant for those two, because as A decreases, the half-life is going to change. As A decreases for a zero order reaction, the half-life is going to decrease. But as A decreases for a second order reaction, the half-life is going to increase, because these two are inversely related. Now for a first order reaction, it doesn't depend on the initial concentration. So because the half-life is independent of the initial concentration, the half-life is constant for a first-order reaction. So answer choice D would be a true statement if this was a first-order reaction. Because ln2 is constant, K is constant, as long as the temperature doesn't change, so the half-life will be constant for a first-order reaction, but it's not constant for a zero-order or a second-order reaction. For the sake of learning, let's analyze answer choice E. The half-life of a second-order reaction, so we're dealing with this equation, is inversely proportional to the initial concentration of the reactant. We know that's a true statement. Now, when we were analyzing part B, we were focused on K. Anytime you increase the denominator of a fraction, the value of the whole fraction goes down. So anything on the bottom of the fraction is going to be inversely related to whatever is equal to the entire fraction. So as we saw in answer choice B, if we increase the rate constant K, the half-life of a second-order reaction would decrease because it's on the bottom. So those two are inversely related. The initial concentration of the reactant is also on the bottom of that fraction. And therefore, if we were to increase the initial concentration of the reactant, the half-life would decrease. And if we were to decrease the initial concentration of the reactant, the half-life would increase. So because these two are on the bottom of the fraction, they are both inversely related to the half-life for a second-order reaction. Number 4, the initial concentration of a reactant in a zero-order reaction is 0.75 m. The rate constant K is 0.015 m per minute. What will be the new concentration of the reactant after 15 minutes? So feel free to pause the video if you want to try this problem. So we're dealing with a zero-order reaction. The straight line equation for a zero-order reaction is the final concentration is equal to negative kT plus the initial concentration. In this problem, we're given the rate constant K. It's negative 0.015 molarity per minute. The time is 15 minutes, so that's T. Let's put that in parentheses. And we're given the initial concentration, which is 0.75 m. Our goal is to calculate the final concentration 15 minutes later. So we could cancel the unit minutes, and so we're going to get the unit in molarity. It's going to be negative 0.015 times 15 plus 0.75. So the final concentration after 15 minutes will be 0.525. And it makes sense because as the reaction proceeds, the concentration of the reactant should decrease. It decreased from 0.75 to 0.525. So that's the answer for part A. Now let's move on to part B. How long will it take the concentration to be reduced to 0.06 m? So this time, we're looking for T. Let's write down what we know. We know the initial concentration is still 0.75 m. We still have the rate constant K is 0.015 molarity per minute. And the concentration is going to 0.06. So that's the final concentration, the new final concentration at some time T. So we're trying to calculate that time T. So let's replace the final concentration with 0.06 m, K with 0.015. We're trying to calculate T and then plus the initial concentration of 0.75. So let's do some algebra. Let's subtract both sides by 0.75. So these will cancel. 0.06 minus 0.75 That's negative 0.69. And the units is molarity. And then it's going to be equal to negative 0.015 molarity per minute times T. So let's divide by this number. So T is going to be negative 0.69 divided by negative 0.015. So T is equal to 46. Looking at the units, we can see that molarity cancels, and T is going to be in minutes. So the final answer for part B is 46 minutes. It's going to take 46 minutes for the concentration to go from 0.75 to 0.06 m. Number 5. Calculate the initial concentration of a reactant that took 4.7 minutes for it to reach a final concentration of 0.15 m. And we're given the rate constant K. So what do you think we need to do here? Well, let's write down what we know. So we don't have the initial concentration. This is what we're looking for. We do know the final concentration. That is 0.15 m. And we know the time that it takes to go from the initial concentration to the final concentration, and that is 4.7 minutes. And we also know the rate constant K. Instead of rewriting it, I'm just going to highlight this. So how can we calculate the initial concentration? Well, first we need to determine which integrated rate law expression we need to use. And to do that, we need to determine the order of the reaction. Is this a zero order reaction, a first order reaction, or a second order reaction? So this problem is a little bit harder because we don't know what order the reaction is. How do we find out? Well, it turns out that we could find out from the units of K. The units of the rate constant K can help us to determine what the order of the reaction is. So the formula that we've used before to get the order of the reaction with the units of K is this one. Now, T to the minus 1, we have that already. That's S to the minus 1, so we don't need to worry about that part. What we're going to do is we're going to set this equal to this part of the unit, m to the negative 1. So that means that 1 minus n is equal to negative 1 because m equals m. Our goal is to solve for n. N is going to give us the order of the reaction. So let's subtract 1 from both sides. These will cancel, and we'll get negative n is negative 1 minus 1, which is negative 2. Multiplying both sides by negative 1, we get that n is 2. So we're dealing with a second order reaction here. Now that we know the order of the reaction, we know which integrated rate law to use. So this is going to be the equation. 1 over A final is equal to positive KT. Remember, the slope of a second order reaction is positive K, and then plus 1 over A initial. So now we could solve for this variable. Let's plug in everything else. So A final is 0.15. K is this value here. So that's 0.0025. Now we need to be careful because notice that K, the rate constant K, has the unit seconds. Here, the time is in minutes. So let's convert T from minutes to seconds. So we have 47 minutes. Always make sure that the units match. And then there's 60 seconds in 1 minute. (47 times 60) is 2820 seconds. So let's put the units here. So this was m to the minus 1, and then s to the minus 1, and then we're going to multiply that by 2820 seconds. So s and s to the negative 1 will cancel. So we're going to get m to the minus 1 here, which is 1 over m. And this is what we're looking for. One divided by 0.15, that's 6.6 repeated. So it's 6.667. And then 0.0025 times 2820, that's 7.05. Now I need to make a correction because I multiplied 47 minutes instead of 4.7 minutes. So it's 4.7 minutes times 60, which is 282 seconds and not 2,820 seconds. So I need to get rid of this 0. So that's 282 seconds that should be here. Now if we multiply these two numbers, 0.0025 times 282 seconds, the seconds will cancel, but instead of getting 7.05, we should get 0.705. So now let's subtract both sides by 0.705. P 6.667 minus 0.705, and that's going to be 5.962, and that's equal to 1 over the initial concentration. Now once you get to this part, the quickest way to solve for the initial concentration is to take the reciprocal of both sides of the equation. To do that, raise both sides to the minus 1. When you raise this to the minus 1, the fraction flips. It flips from 1 over the initial concentration to the initial concentration over 1, which you could simply write initial concentration of A. Now here, this was 5.962 before. When you raise it to the minus 1, it becomes 1 over 5.962. So if we take 1 and divide it by 5.962, we're going to get the answer that we're looking for. So the initial concentration of A is 0.1677 m. So this is the answer to the problem. So when you get questions like this, if the order of the reaction is not specified, take a look at the units of K. If you're given the units of the rate constant K, you could determine if it's 0 order, if it's first order, or if it's second order. Now let's move on to our next problem, number 6. The data table below shows the concentration of a reactant with respect to time for a 0 order reaction. What is the value of the rate constant K? Now what you need to know is that the rate constant K is equal to the slope of the line if you plot A versus T for a 0 order reaction. If you plot this on a graph, you should get a straight line. So A is on the y-axis, time is on the x-axis, and it's decreasing, which means that the slope is negative. And K has to be a positive number, so K is equal to the negative slope, or slope equals negative K. So let's calculate the slope. The slope is the change in y divided by the change in x. So the y values are concentration values, and the x values are time values in this example. So let's just pick two numbers. Let's use the first and the last result. So the final concentration is 0.16 and the initial concentration is 0.8. The change in time is 40 seconds. So 0.16 minus 0.8, that's negative 0.64 divided by 40. And so it's going to be negative 0.016 molarity per second. So that's the slope, which means that K is positive 0.016 molarity per second. So remember, the slope is equal to negative K. K is always a positive number. Number 7. What is the half-life for a reaction with a rate constant K of 0.0045 seconds to the minus 1? So what do you think we need to do here? Well, the first thing that we need to do, like the last problem, or rather 2 problems before that, is we need to determine the order of the reaction, because it's not given to us. So like problem 5, we need to pay attention to the units of K. So based on those units, s to the minus 1, what is the order of this reaction? So we know the formula is going to be m raised to the 1 minus n times t to the minus 1. And we're going to set that equal to the units of K. So this is a unit of time, and the same is true for that. But we don't see an m here. If you don't see an m, it's really m to the 0, because anything raised to the 0 power is 1. So what we're going to do is we're going to set the exponents of m equal to each other. So 1 minus n is equal to 0. If we add n to both sides, we get that n is equal to 1. So this is a first order reaction. When you don't see units of molarity or moles or liters, if you just see time to the negative 1, that's an indication of a first order reaction. So anytime the rate constant K has units such as s to the minus 1, minutes to the minus 1, hours to the negative 1, with no molarity, no moles, no liters, you know you're dealing with a first order reaction. So now that we know the order of the reaction, what formula can we use to calculate the half-life? The half-life equation for a first order reaction, it's equal to the natural log of 2 divided by the rate constant K. The natural log of 2 is 0.693147. The rate constant K is 0.0045 with the unit seconds to the minus 1. So let's go ahead and divide those two numbers. So we get that the half-life is approximately 154 seconds based on the unit that we have here. So that's how we can calculate the half-life of a first order reaction. Number 8. Which of the following straight line plots correspond to a first order reaction? Let's look at answer choice A and B. Both plots have A versus T, which corresponds to a zero order reaction. Here, the slope is positive K, and for this one, it's negative K. Now we know for a zero order reaction, the slope is negative. So answer choice B corresponds to a zero order reaction. Answer choice A doesn't correspond to anything. Now for a second order reaction, we're going to get a straight line plot if we graph 1 over A versus T. And the slope for this one is positive K. So answer choice C corresponds to a second order reaction. Answer choice D is what we're looking for. This corresponds to a first order reaction. We're plotting ln A versus T, and we have the correct slope. The slope is negative K. So answer choice D is the correct answer for this problem. Number 9. The rate of a certain reaction with units of molarity per second increases by a factor of 4 when A doubles and increases by a factor of 27 when B triples. Which of the following represents the units of the rate constant K for this reaction? Well, let's begin by writing a rate law expression. So the rate of this reaction is going to equal the rate constant K times the concentration of A raised to some variable times the concentration of B raised to some variable or number. Now let's focus on A. When A increases by a factor of 2, the rate increases by a factor of 4. So when A doubles, the rate goes up by a factor of 4. So would you say it's zero order in A, first order in A, second order in A, or third order in A? Well, 2 to the what power is 4. We know that 2 squared is 4. So this tells us that it's second order with respect to A. Now, looking at the second part of the problem, it says that when B triples, or when it increases by a factor of 3, the rate of the chemical reaction increases by a factor of 27. So 3 to the what power is 27. We know that 3 to the third power is 27. 3 times 3 times 3 is 27. So it's third order with respect to B. Now, what is the overall order of the reaction? The overall order of the reaction is the sum of these two exponents. So it's fifth order overall. Now that we know the overall order of the reaction, we could use that shortcut technique to get the units of K. Recall the units of K is m raised to the 1 minus n, where n is the order of the reaction, times t raised to minus 1. So n is not 4, n is 5 rather. And the time is in unit of seconds, so this is going to be s to the minus 1. We simply replace t with whatever time unit we see in the reaction rate. So it's m raised to the negative 4, s to the minus 1. Let's save this answer. So if you were to ever forget this formula, here's another way in which you can get to this point. So in the rate law expression, isolate k. To get k by itself, we need to divide both sides by this. So we're going to get the rate constant k is equal to the rate of the entire reaction divided by a squared times b to the third power. So at this point, what you want to do is you want to plug in the units. The unit for rate is molarity over seconds, or you can say molarity times seconds to the minus 1. The unit for A is molarity, but it's squared. So you can write that as m squared or simply m times m. So that's for A. For B, it's m to the third power. So I'm not going to split it for that one. The reason why I split this into m times m is because I want to cancel one of the m's. So we can see that we have m to the 4 left on the bottom. 1 plus 3 is 4. Now we can move this to the top, and then we get the units of k as being m to the negative 4, s to the minus 1. So you get the same answer as what we got here, but this is just simply a shortcut technique. But you can always do it this way if you want to, if you ever forget. Now, this does not look like any of the answers that we have here. So we need to adjust our units. Molarity is moles over liters. This is moles to the first power, liters to the first power. We're going to move liters to the top. So m to the first power is moles to the first power times liters to the negative 1 power. Now, m to the negative 4. What we're going to do is we're going to write that as m to the first power raised to the negative 4. Because when you raise one exponent by another, you need to multiply. 1 times negative 4 is negative 4. So now we can replace m to the first power with what we have here because it equals m to the first power. So we're going to get moles to the first power times liters to the negative 1 raised to the minus 4. Now we're going to distribute negative 4 to these exponents. So first we have 1 times negative 4, which is negative 4. And then negative 1 times negative 4, which is positive 4. And typically, the variable with the positive exponent is usually written first. So m to the negative 4 can be rewritten as L to the 4 times moles to the negative 4. So now all we need to do is add our seconds to the minus 1. So m to the negative 4 times s to the minus 1 is liters to the 4th power times moles to the negative 4th power times seconds to the negative 1 power. So We can represent the units of k like this or like that. But looking at our answer choices, we have it in this form. Therefore, answer choice C is the correct answer. Number 10. What is the overall order of a reaction with the units liters cubed, moles to the -3, seconds to the -1? So with this problem, we're kind of going backwards here. So let's see if we can do this. We know that molarity is moles over liters, which is the same as moles to the first power times liters to the -1. Now, if we were to raise both sides to the -1, let's say if we were to raise this to the -1 and that to the -1, we'll get that m to the -1 is equal to -1 times -1 is +1, so that's liters to the first power, and then 1 times -1 is -1, moles to the -1 power. So you may want to be familiar with these expressions. So molarity to the first power is moles to the first power times liters to the -1. But molarity to the -1 is liters to the first power, moles to the -1. And in this example, notice that liters has a positive exponent. So liters cubed moles to the -3, what is that equal to? Well, if we factor out an exponent of 3, we'll get liters to the first times moles to the -1 raised to the third power. So these expressions are equivalent. We just factored out 3 from the exponent. Now, these two are the same, so we can replace what's here with m to the -1. So we have m to the -1 raised to the third power. So this is m to the -3. So liters cubed moles to the -3 is m to the -3. So now let's write everything that we have here. Liters cubed moles to the -3, s to the -1, that's going to be m to the -3 times s to the -1. Now let's set this equal to our general equation, m raised to the 1 minus n times t to the -1. So we don't need to worry about this. We know the time is in seconds. What we need to do is set these two equal to each other so we can solve for m. So m to the -3 is equal to m raised to the 1 minus n. Now since m is the same, we can set the exponents equal to each other. So -3 is equal to 1 minus n, and let's subtract both sides by 1. -3 minus 1 is -4. If -4 is equal to -n, then we just got to multiply both sides by -1, and we'll get that positive n is equal to 4. So we can say that this reaction is fourth order overall. So answer choice E is the correct answer.